Apologize for being a couple of minutes late. Let's jump right in. So today we're going to be covering as much of chapter 5 as we can, which is, as previously, is all about resistors, capacitors, and MOSFETs, and strategies that we can use or phenomenon that we need to be aware about while we are designing a analog CMOS integrated circuit. So our first topic that we are going to speak about today is let me make sure my volume is turned up so I don't run into it. Okay. In case you guys have a question, I can actually hear you today. So about the temperature coefficient of resistance. As most of you are aware, in a semiconductor, the amount of free charge carriers that are available is highly dependent on temperature. And so to that end, when we make resistors, particularly out of the N-well, we should see some changes in the resistance due to temperature. So the first thing that we're going to talk about is the resistivity. So as you hopefully recall from even way back in circuits 1, or potentially even your engineering 120 series, if you were here for that, resistivity is a material property how difficult it is to pass a current through a medium. Mathematically, especially in, this is from your solid state classes, the electrical resistivity is defined to be a fraction that is simply 1 divided by Q mu n times n plus mu p. I think I might have used mu h earlier, but I'm going to use mu p now, and I'll make sure to describe that, times p, where Q is the fundamental charge, so 1.6 times 10 to the negative 19 coulombs. Mu n is the electron mobility, measured in centimeters squared per volt second. I know it's an odd unit, but that's what it is. N is the electron concentration. Measured in electrons per centimeter cubed. And it's simply ND in N-type materials. And we have mu p, which is the whole mobility. Also having units centimeters squared per volt second. And we have P, which is the whole concentration. Which is also measured in centimeters per centimeter cubed. And it's Na in type. So before we move along here, does anybody recall what the electron mobility or the whole mobility, like what the concept of mobility in a solid state circuit really means?
If I'm thinking correctly, it's the scattering, right? Like the atoms hitting each other and then they get scattered throughout the crystal lattice, something like that.
So that's like that's related to mean free path and a couple of other things that are also related to mobility.
It's
but
the sorry.
Go ahead.
Is it the average velocity that like the electron can get to before it hits?
So it is related to the carrier velocity, but it's the carrier velocity divided by the applied electric field. So you guys are all close, so that's great that you've remembered something. Okay, so we're going to need to keep that in mind a little bit as we further discuss things here. So let's see, right here. Draw it out. There we go. So our mobilities, mu n and mu p, as well as our concentrations n and p, all depend on the temperature. So what we typically see is that mu n and mu p decrease as temperature T increases, and it's for the exact reasons that was mentioned by Aiden and Grant. There are more lattice vibrations at higher temperatures. Which lead to more scattering events. And let's see that this causes the carrier velocity to decrease for a fixed electric field. So if we don't change the difference, if we don't change the field that we're applying, but we increase our temperature, increased electric field. I'm trying to write things down and talk, and the words are different, and it's screwing me up. All right, so if we hold the electric field constant so that there's the same amount of push on our charge carriers, whether it be a hole where the holes move in the direction of the electric field, or electrons which move opposite the direction of the electric field. As the temperature increases, the increase in lattice vibrations effectively means that electrons and holes are going to bounce around more, and they're going to have a much shorter time between scattering events, which leads to their mobilities being decreased. Now, what's interesting is that N and P our concentrations both increase as the temperature T increases. So as our temperature goes up, we have an increased thermal generation of electron hole pairs, which I'll simplify as EHP. And we see that more electrons are able to move from the valence band to the conduction band, leaving behind holes. Leaving, that's not big, so it's kind of, right? So the increase in thermal energy causes more electrons to jump out of the valence band, leaving behind holes, which is what the thermal generation of electron hole pair mechanism actually is. So these are kind of just two ways of stating the same thing. So from this, we have two conflicting things happening, right? If we look at our original equation up here, we should see that as mu n or mu p increase, our resistivity, so our denominator is going to get larger, right? And so our resistivity should go down, meaning we're conducting well. And if n or p increase, we should see the same effect. But we have two different phenomena based on temperature, where one causes a value to decrease, which would increase the resistivity, and the other one causes the values to increase, which would increase the resistivity. So we have to look at which effect is dominant. So if mobility is the dominant effect resistivity, the material will have a positive temperature coefficient of resistance, which we'll call TCR1. So when T increases, rho E increases. Instead, if the carrier concentration is the dominant effect, on resistivity, the material will have a negative temperature coefficient of resistance. So negative temperature coefficient means when the temperature goes up, the resistance or the resistivity goes down. So in general, The behavior of semiconductors looks something like this. On this axis, we have the resistance as a function of temperature. On this axis, we have temperature, which can be measured either in degrees Celsius or Kelvin. And at critical temperature, give me just a second, I can't read my writing there on that graph. T naught, that's what I thought it was, okay. So this temperature T naught is our room temperature. And we have, here's the resistance at temperature T naught. The slope of this guy is the change in resistance with respect to the change in temperature. We will observe that the resistance R as a function of temperature is the resistance at temperature T naught multiplied by 1 plus 1 divided by R at T naught times delta R over delta T. Our slope there, where this guy is our temperature coefficient of resistance multiplied by the deviation in temperature away from our room temperature measurement. So this is how we're going to see resistance change as a function of temperature in our circuits. So if we have an N-well resistor with a TCR1 of approximately 2,400 parts per million per degrees Celsius, let's just say has a for a 10K determine the resistance variation as T ranges from 0 degrees Celsius to 100 degrees Celsius. So this would be a fairly standard, well, actually 100 degrees Celsius might even be a little low. But I just know, like measuring my computer processor temperatures, because they tend to get dusty and overheat. I've seen temperatures of my CPU reach around 90 degrees Celsius and my GPU up to 115 degrees Celsius. So I've never had them freeze on me or anything, but I've definitely seen them hit 100 C or more. So it would be interesting to see what kind of variance that we have. All right, so the resistance at 0 degrees Celsius is simply going to be our nominal value of 10 kiloohms multiplied by 1 plus our temperature coefficient. So 2400 parts per million is the same as 2.4 parts per thousand, so 0.0024 per degree C. Multiplied by our temperature variation, so 0 minus room temperature 27 degrees Celsius, and this is going to give us a value of 9.352 kiloohms. So just for the sake of argument, 9.352 divided by 10,000, we have a decrease in resistance of 6.48%. If we're looking at the high end, we're now going to have 100 minus, so 100 degrees C minus 27 degrees C. And this is going to give us a value of 11.752 kiloohms. So it's jumped up quite a bit. An increase of positive 17.52%. So the variation is actually pretty large, plus or minus pretty close to 25% swing over this 100 degrees C interval. So we can see that the temperature for an N-well resistor can change pretty drastically based on its temperature operating conditions, which for, again, analog applications may not be the best idea, right? If the value of the feedback resistors and things like that is critically important, having this large of a change just due to the environment that the chip is going to be in could be very detrimental to the operation. All right, so now let's talk about the voltage coefficient of resistance. If I can write. All right, so for an N-well resistor, give me just a second. I'm going to save this as chapter 5 notes and then restart my program because it's giving me that weird error thing again. Solved it. So for N-well resistors, the potential difference across a resistor causes variations in the depletion region of the N-well P-sub-junction. It's going to look a little something like this. So let's say this is a cross-sectional view. So we have our top and bottom surface of our P-sub. We have our N-well in green, and so let's see. If we apply, let's start there. So let's say that, and I'm just drawing a simple terminal here, 5 volts on this side of our resistor and 0 volts on this side of our resistor. Well, we'll see that our junction should be significantly, and we're also assuming that our substrate is grounded, so let's start there as well. So we just drop a little ground symbol here. So on the left-hand side, the junction is more reverse biased than the right-hand side. And so that increase in reverse biasing should give us kind of an odd profile. So we should see that over here, it's significantly thicker than it is on the left-hand side. And we'll see that exact same effect on the P side of the junction as well. So really thick, tapers off, and is effectively just CJ naught on the right-hand side there. So since the size of the depletion region changes, where the depletion region is effectively devoid of free charge carriers, this is going to cause the effective thickness of the N-well to vary over its length. Which in turn varies the sheet resistance of the N-well. Remember that the sheet resistance of the N-well was dependent on the thickness of the well being constant. So if the thickness isn't constant, then the sheet resistance isn't constant either. And we should see that as the reverse bias voltage increases, the average resistance of the N-well also increases. This relationship is known as the voltage coefficient resistance, voltage coefficient. VCR1, where VCR1 is equal to 1 over the resistance with an unbiased junction multiplied by the change in resistance divided by the change in voltage. I've got something in my notes here that says where V is the average voltage applied to the resistor. Okay, so I think that's actually should be delta V. Let me double check that. Yeah. Sorry. Sum of the voltages at each end of the resistor divided by 2. So you can get an equation for the resistance as a function of voltage. And it's going to look very similar in form to that for our resistance as a function of temperature. R as a function of V is R times V naught, 1 plus VCR1 V minus V naught. All right, so let's work another quick example. We want to calculate the average resistance of a nominal 10 kilo ohm and well resistor at 27 degrees Celsius, so room temperature, for an average voltage across the resistor. Of 0 volts, which the answer to that one should be pretty obvious, 5 volts, and 10 volts. If VCR1 is 8,000 parts per million per volt. All right, so with 0 volts average voltage applied across the resistor, meaning if one side was pinned to ground, the other side is also pinned to ground, it shouldn't be particularly crazy to find that we don't observe any voltage coefficient of resistance effects. All right, so let's see, 8,000 part per million is 8 parts per thousand. And that has units of per volt multiplied by our change in average voltage, gives us 10 kilo ohm. Nothing crazy there. If our average voltage applied is 5 volts, we should see some difference now. Writing's getting terrible. And this will give us 10.4 ohms. So we have an increase of 400 ohms of average resistance across our N-well resistor as we apply 10 volts to one side and ground to the other. And then lastly, with a 10 volt average resistance, we should see that the change in resistance has doubled, since it's a simple linear relationship. And we get 10.8 kiloohms. So we can observe that the resistance increase due to the voltage coefficient is typically much smaller than temperature coefficient effects. Anybody care to posit an idea why? Oh, wait, no, that shouldn't be a question mark. All right, so for instance, in the C5 process, our maximum allowable voltage is for our devices are going to be 5 volts. That's what the process is designed for. Anything over that would potentially cause the gate oxide region of our transistors to break down, rendering our transistors inoperable, right? So if the smallest average voltage that we can apply to a resistor in our process is 2.5 volts, then that means that we're going to see, a fairly small change in the resistance value. Whereas the temperature is dependent on our strategies for heat dissipation and a whole other host of things. So even though it seems like our voltage coefficient is larger, 8,000 parts per million per volts, than the temperature coefficient we discussed before, which was, I think, 2.4 parts per million per degrees Celsius, we should see that the temperature is going to vary much more widely in operation than the voltage will. All right. So let's see, it's 8:42. So let's take 5 minutes or so, and then when we reconvene, we'll start talking about poly capacitors. All right, answered a couple of emails and all that jazz, so I'm ready to get cracking now. So this is still within the same chapter, but it's a wildly different topic. So I'm going to start over on a new sheet of paper here. Excuse me. So now we're going to move on to poly 2 capacitors. Yes. So capacitances may be formed by overlapping the poly 2 layer above the poly 1 layer, or the poly layer. And the rules for this are in page 31 of the SCMOS. On pen, work with me. A simple layout would look something like this. Where, let's see, I've been using pink for poly 1, I believe. So from a layout or top-down view, it might look something like this. Stop misbehaving. So this is our poly or poly 1 layer. And then obviously we would need to have some metal connected as one to serve as an electrode. And we would put in several bias to make the contact between the metal 1 layer and the poly layer. For poly 2, I don't remember exactly what color I used. So for now, I'm going to use brown. So this might be our poly 2 layer. And we would also need to connect poly 2 to metal 1 for our contact on our bottom electrode, or top electrode, excuse me. Poly 2, those regions can't be as, the overlap regions can't be as large as that of poly 1 because of the design rules, which means we're never going to have true parallel plate capacitors of the exact same plate size. So we're just going to have to use the area of our top electrode to count for that. Anyway, so from a side view, it may be a little bit easier to see what's really going on here. we'll have our field oxide layer. I can draw a straight line. Sorry, this is the vet's office. My dog is in the hospital. I need to take this real quick. Alrighty, sorry, they were just giving me an update about how he's doing this morning. Okay, so now this large layer right here, oops, and I'm exaggerating the thickness of the insulation layer here, is where our poly layer is, poly. And so poly 1 lays directly on top of the field oxide layer. And then poly 2, which I'm doing in brown, is physically distanced from it by a bit and buried within that insulation layer. Like so. Then we would finally see up above our metal 1 layer here and here. And the connections are made using these. Like so. All right. So we can see that there is obviously an area of overlap between the two, and we form a capacitance here. Now, what's interesting is that there are also parasitic capacitances that are going to come about due to this, right? So because our substrate is doped and it is lightly conductive, we actually form a parasitic capacitance here, C poly actually I've screwed something up here, but that's okay. So what I screwed up here is that the poly 1 layer needs to completely overlap, and I didn't make it overlap all the way, so it should be drawn something like this. It's going to extend out to here. All right, sorry about that. And that would have, if we had been drawing this on the layout tool, I would have got an error telling me that I did it wrong, but we're not doing that just yet. So we have this parasitic capacitance between the poly layer and the substrate. We also have a parasitic capacitance between the metal 1 layer and the substrate over here, as well as over here. If we had additional metal layers, because obviously metal 3 is how we're going to be able to send signals to and from this capacitor. We may have some associated parasitics there as well. So developing a single capacitor on purpose, the one between the poly 2 layer and the poly 1 layer, has generated 3 additional parasitic capacitances, but we can observe that the distance between the conducting plates in each of these cases is significantly larger. So while they will have some effect, our dominant intentional capacitor should be considerably larger. All right, so let's circle back around. The thin oxide layer between the poly and poly 2 layers is made from silicon dioxide and is approximately the same thickness as the transistor gate oxide. Which I believe, I don't have the number in front of me, but it's on the order of, at best, a couple of nanometers. It's very, very small. In the C5 process, the oxide capacitance per area is around 950 attofarads per micron square. Maybe a little bit more, maybe a little bit less, depending on the actual fabrication run, but somewhere in this area is reasonable. So when we were dealing with the metal 3 to substrate capacitances, we saw that that was something like 26, I think, attofarads per micron square. So this is, you know, significantly larger, like roughly 30 to 40 times larger. All right, so we circle back around to our parasitic capacitances. We can see that the dominant capacitance is the bottom plate parasitic. So the parasitic forms between. So let's take a look at an example. First, it's telling me that it's connecting to the cloud server. So are any of you guys actually still able to hear me? Let's start there. Or am I just talking to nobody?
We can hear
No,
you.
we can hear you.
Okay, great, cool. I just wanted to make sure I'm not completely ranting to nobody. Alrighty, thank you. So capacitance of a poly to poly 2 capacitor if poly 2 plate has dimensions of 20 microns, or excuse me, not 20 microns, 20 lambda by 50 lambda for a C5 process And then how does the bottom plate capacitance compare to the desired capacitance value? Desired. All right, so the first thing that we're gonna, well, we could determine the poly 2 capacitance right now because we know the value of the oxide capacitance per unit area as well as effectively the area. But we don't quite have enough information to determine the poly to substrate capacitance because we don't know what the area of the bottom plate is. So let's take a moment and find this in our design rules. So that means I have to find the design rules in my, let's see. Maybe they're here. Well, I know exactly where I put them. So, I put them in Moodle, so let's just do that. All right, so here we have this, and then here, resources, and then SCMOS design rules. And so I happened to write down a page number, page 31. All right, layout rules for poly 2 for capacitors. So in our submicron process, the minimum poly overlap, which is governed by rule 11.3, says that we have to be 5 overlap on all sides, right? So we can see in the little figure down here that if our poly 2 plate is here, 11.3 tells us that we need to be 5 in this direction. We also need to be 5 in this direction and the other directions as well. So from that, what are the dimensions of our poly 1 plate going to be? So if the poly 2 is 20 by 50, and I'll make a crappy drawing of that real quick, so let's see. So here's our poly 2. This is 20 lambda. This is 50 lambda. If we need to extend by 5 on both sides, so in the vertical direction and in the horizontal direction, then that means that this guy is 60, and this guy at a minimum is 30, right? If I extended by 5 on both sides. So 20 plus 5 is 30, 50 plus 5 is 60. So I feel like I have satisfied it. I am sharing the screen and stuff, right? So you guys have some idea of what I'm doing.
Yes.
Yeah.
All right, cool deal. Okay, so from that, I guess we'll have to go down here. The capacitance of our poly to poly 2 capacitor is going to be Cox prime times 20 lambda times 50 lambda is going to be 950 times 10 to the minus 18 farads per micron squared. 20 times 50 is 1,000, and then I'm going to have 0.3 microns squared, and this gives me a value of, let's see, 950 times 10 to the minus 18 times 1,000 times 0.3 times 10 to the minus 6 quantities squared. I messed something up here. Oh, I don't need to do the times 10 to the minus 6 because it's per micron. Sorry, that's my fault. Alrighty. 85.5 femtofarads. Now we also need to know the capacitance of the poly layer, or the area capacitance of the poly layer with respect to the substrate, which give me just a second to find that value for you. I think I have it as 86 attofarads per micron squared, but I want to just A, show you where I'm getting that, and B, make sure. I think that was tacked on to the end of an exam, but not that one. There we go. So we're looking for poly to substrate. Actually, yeah, poly to substrate is going to be this guy right here, which is 86. This is from a fabrication run. This 893 right here is the poly 2 to poly 1 from this particular fabrication run. So we could use that value if we wanted to for our other area. I guess that'd make things more accurate, but this will be okay. Let's see. There's no data for poly to substrate fringe capacitance, and there's no data for poly 2 to poly fringe capacitance as well. So they're either so small they don't matter, or for whatever reason they didn't test for those parameters. So we're going to assume here that our fringe capacitances are 0. All right. So 86 is the number that we'll be using. So this is C poly to sub. So we need our capacitance per unit area times our dimensions, which in this case is 30 lambda times 60 lambda. So that's going to give us 86 attofarads per micron squared times 1800, which is 30 times 60, times 0.3 microns squared, and this gives me 13.93 femtofarads. So the ratio of these two guys is 17.33%. So our parasitic capacitance is roughly 1/6 that of our designed capacitance, okay? So that's a pretty significant number. And you know, we're gonna have to employ different techniques to try to mitigate some of these capacitances, parasitic capacitances, and we'll talk about that a little bit later. But now that we've defined how a poly-poly capacitor is made, let's talk about how its temperature, or excuse me, its capacitance also varies with temperature. So the capacitance of a poly to poly 2 capacitor varies with temperature and voltage. So the capacitance as a function of temperature is the capacitance at room temperature multiplied by 1 plus the temperature coefficient of capacitance multiplied by the variance in temperature, where TCC is this, which for our process has approximately a value of 20 parts per million per degree C. So 20 parts per million per degree C means that we're going to see a much smaller variation in capacitance due to temperature changes than we saw as a variation in resistance due to temperature changes. We can also see that the capacitance as a function of voltage is the unbiased capacitance multiplied by 1 plus the voltage coefficient of capacitance multiplied by the variation in voltage, where V is the plate voltage difference, so the difference in electric potential between the two plates. Where VCC is 1 over C dC dV is about 10 parts per million per volt. So the extremely low values of TCC and VCC mean that poly to poly 2 capacitors are extremely stable. So we don't see much variation in capacitance. Alrighty. Now let's start talking about metal capacitors, which we mentioned a little bit before, I believe. So, in addition to poly 2 capacitors, we can also lay out capacitors using metal layers. So the most simple way to look at this would be something like this. So here is our P-type substrate. Here is our field oxide. Here's our poly layer. This guy is where metal 1 is. And so we can put a metal 1 layer down. And then up here, metal 2. And it should be fairly obvious that when you put two metal plates on top of each other, they form a parallel plate capacitor, where we'll also have this guy here, which is C metal 1 this up. So we're going to have a bottom plate parasitic capacitance here as well. So typically, metal capacitors exhibit much smaller capacitances. Than poly to poly 2 capacitors. Since the spacing between the plates is significantly larger. So if we pop back over to this guy, let's erase that and erase that. So the area, so if we're looking at, let's see, this one. So metal 2 to metal 1 is 33 attofarads per micron squared, whereas poly to poly 1 was 893, right? So just to be clear, 893 divided by 33, 27 times larger, or the metal to metal capacitance is going to be 27 times smaller. We can see metal 2 to metal 3 is roughly the same value, you know, a difference of 32 and 33 attofarads per micron. That's fairly straightforward. The difference why metal 3 to metal 1 is so much smaller is because it's effectively a metal 1 to metal 2 capacitor in series with a metal 2 to metal 1 capacitor. So when capacitances are in series, we get smaller numbers, which hopefully you guys all remember. And let's see, there is some information regarding fringe capacitances between metal 2 and metal 1, as well as, let's see, oh, that's poly and metal 2. So metal 2 and metal 1 here, and metal 2 and metal 3 here. So those capacitance values are much, much smaller, which means that large chip area is required to implement large capacitors. And we'll actually talk about ways to mitigate that, I think, today. Yeah. Yeah, let's talk about that actually right now. All right, so we can minimize, oops. Actually, let me talk about something else before we jump into that. So it makes more sense. All right, so as we talked about a few minutes ago, there is a bottom plate capacitance here, right? So there's a capacitance formed between metal 1 and metal 2, and there's also a capacitance formed between metal 1 and the substrate. So the issue here is that the distance between the metal 1 and metal 2 plate is almost the same as the distance between the metal 1 and the substrate. And since the spacing between them are the same, that means that the parasitic capacitance can be almost as large as the design capacitor. So if we take a look at a quick example problem, let's calculate the capacitance of a metal 1 to metal 2 capacitor formed with 100 micron by 100 micron metal plates. How does the bottom plate parasitic capacitance compare to the designed capacitor value? All right, so our capacitor formed between our metal 2 and metal 1 plates is going to have an area component and a fringe component, all right? Because we have data available for the fringe. So it's likely that since the poly 1 and poly 2 capacitors are physically spaced so close together, like on the order of a couple of nanometers versus the order of hundreds of nanometers, the fringe fields aren't dominant or even really present because the electric field is so well maintained because the distance is small. The further you get the plates apart, the more the fringe fields are going to allow to try to expand out from the plates. All right, so we're going to have the area coefficient between metal 1 and metal 2 multiplied by the plate area plus the fringe coefficient between metal 1 and metal 2 multiplied by the perimeter. So what values should I use in this first equation here, right? So I'm looking for the area coefficient between metal 1 and metal 2. So this 33. And then I'm looking for the fringe between metal 1 and metal 2, which is this guy right here, 47. So I'm going to have 33 attofarads per micron squared multiplied by 100 microns squared plus 47 attofarads per micron multiplied by, it's a square plate, so the perimeter is simply 4 times the length of one side, so 400 microns. And this gives me a value, I believe, of 348.8 femtofarads. So before we even go forward with calculating the parasitic capacitance, I want to talk about something here real quick, right? So we have 348.8 femtofarads as our capacitance. In our poly-poly capacitor example up here, we had 85.5. So 348.8 divided by 85.5 is a difference of roughly 4. So, or not a difference 4, but the metal capacitor has 4 times the capacitance. That being said, the total area here, right? So 20 lambda times 50 lambda. So that's 20 times 0.3 times 50 times 0.3 is 90 microns squared. Whereas here, our area of our plate is 100 microns by 100 microns. So that would be 10,000 microns squared. So 100 times 100 divided by 90. So the area of the metal plate capacitor is literally 111 times as large, while only giving us a 4 times increase in capacitance. So that's how disparate making a poly-poly capacitor versus a metal capacitor is. Okay. Metal 1 substrate, we're going to have the same basic thing here. We're going to have an area component and a fringe component. Times P. So let's pop over and look at what those values are going to be. So fringe substrate to metal 1 is 50. Area substrate to metal 1 isn't given. That's weird. Hold on. Maybe I'm looking at something wrong here. Yep, I'm totally looking at something wrong here. Area substrate to metal 1 is 28. Okay, yeah. So we need this guy as our area and this guy as our fringe. And we get 300.4 femtofarads. So the parasitic capacitor is actually 86.12% as large as our desired capacitance, right? So that's fairly appreciable. Actually, much more so than fairly appreciable. It can be a huge problem. So to mitigate that, and also to mitigate needing a very large footprint, now let's talk about our last little topic of the day, which is a stacked or interdigitated capacitor. So yeah, I think that'll be enough room. Here's our substrate. Here's our field oxide layer. Let me sneak them in like this. So this is the field oxide and the poly layer. I'm just smushing them down so I have enough room to draw what I want to draw. This is the layer where metal 1 would reside. Here's where metal 2. Up here is where metal 3 might be. Metal 3. So we might do something like this. Put a metal 1 layer like so. And then we have a metal 3 layer directly overlapping it like this. And these are actually going to form one electrode. And so to facilitate that, I need to go through the metal 2 layer like this. Now I also will have a metal 2 electrode like so, and to get access to putting a signal on it, we'll need something here like so. And so what this does is it effectively, I'm bending one electrode around this central electrode. So that's what's called a folded capacitor. And I form two intentional capacitances here. This is between M3 and M2, and here is between M2 and M1. And then I also still obviously have my bottom plate parasitic, M1 sub. But in stacking the capacitor plates like this, I can actually use a smaller plate on the bottom, but still get a large capacitance value. Excuse me, because effectively I'm putting these two capacitors, CM3 and M2, and CM2 to M1, they're electrically connected in parallel. So if we find the overall capacitance of our stacked capacitor and compare it to our bottom plate capacitance, so let's just formally write this down. Of the stacked capacitor if the area of overlap between the metal layers is 100 microns, sorry, not lambda. So effectively, we're going to have the same bottom plate capacitance and the same capacitance between metal 2 and metal 1, but we're now going to have a capacitance between metal 3 and metal 2, which we'll use so let's see. So metal 2 to metal 3 is at 32 and 52. So those are our two coefficients. So let's jump back over. So we're going to have 32 attofarads per micron squared times 100 microns squared plus 52 attofarads per micron times 400 microns. This is going to give us 340.8 femtofarad. So 340.8, I don't know why I started on a new sheet, oh well, which is very, very similar to this value. So we're effectively doubling the desired capacitance by adding this extra layer, which makes sense because we're adding an extra plate of the same size. And so that in turn, so C stack is 340.8 plus, gosh, it was just right there, 348 point something. 8. Six 89.6 femtofarads. And so now our parasitic capacitance, CM1 to substrate divided by our stack capacitance is only 43.56%. So still significantly appreciable, but much less than it was previously. So that's, again, as I mentioned above, this is a tried and true method of minimizing the parasitic capacitance of your metal capacitors, which you may wind up putting some in your design just because you might need, one of the downsides of the poly-poly capacitor is that it's harder to make small capacitance values with it. So you may wind up making a metal to metal capacitor as what's called a compensation capacitor, which will help with phase drift in your op amp. Anyway, so this is a way to do that without including or without adding too much parasitic capacitance and also minimizing the footprint. All right, so I got 5 minutes left, so let me just talk briefly about what's going to be happening next week. I have roughly 4 or 5 pages worth of notes to cover next week before we actually start jump into to doing some layout stuff. So I'm going to put a link on the course's Moodle page to where you can download Electric. We're going to be focusing primarily on layout, so it's not super important that you have LT Spice installed because we won't be doing any, gosh, I'm trying to think of layout versus schematic checks or anything just yet. I want to make sure that we're all on the same page with how to use Electric and all that kind of stuff before we really get into the nitty gritty of our schematic design there. Because you're probably much more familiar with at least, you know, looking at and reading schematics based on your years of electrical engineering education than you are with actually creating layouts. So anyway, next week we're going to cover the last little bit of chapter 5, which is on MOSFETs. Then we'll probably spend 2 full class periods or thereabouts working with Electric and doing some layouts. So I might have some sample circuits that we're going to try to lay out with some transistors and maybe making capacitors and all that kind of jazz too. And then I'm going to give you your first take-home test probably at the end of next week or the very beginning of the week after that. You'll have a week or so to do it. And while you're working on that take-home test, we're going to start on the actual where we're going to have to use a lot of math side of things, analyzing circuits and all that kind of jazz to figure out how these different building blocks of our multi-stage operational amplifier are going to behave. So yeah, in roughly a week's time, we're going to see kind of a drastic shift in focus from all of this stuff on how the different layers interact back to how do these circuits work, how can we combine them to make larger scale building blocks to do what we need in order to design an op amp. All right, I will catch you guys next Tuesday. I'm going to try to get all the video lectures and all that kind of stuff that we've been having uploaded, as well as, like I said, and Diego reminded me of in senior design the other day, I keep talking about putting homework assignments up for you guys to look at, and then I never actually do it. So expect several of those up over the weekend as well. And again, they're not to be, they're not for a grade or anything. They're just reminders of what I expect you to know about each topic with regards to the test. All right, that's enough ranting out of me. Again, thank you all for showing up, and I will catch you next Tuesday. And if Grant's still on, could he hang out for just a moment?